Okay, as I was saying, the bottom. So what is this area? So it's this triangle. So this 3 triangle. So this is 9A. And this triangle here. So now we have this. Now we pretend this whole thing is shaded. But we have to subtract this. So let's subtract this entire small triangle, which is 4A because the sides are 2 times as long. But then we have to add this back. Let's add A back. So what do we get? So what did we find then? We found that the entire thing, so this entire thing, if it's 3x, the area is equal to 9A, because it implies that 3 squared A. Now, if we're looking at the 2x case, we know the area is equal to 2 squared A, which is equal to 4A. But now if we subtract the entire thing from this, we're left with a shape that looks like this. But we still have to account for the top triangle here. So we have to add that back. And now we already established that area is A. So we can take this, subtract the white, and add back what we still need to get 6A. So you get 6A over 16A, 3/8. And that's your answer. Okay. Moving on to number 3. So there are 138 students. And we want to find the total number of unique combinations of the letter pairs. So how many more students are required to guarantee that at least 2 students whose initials form the same ordered pair? So how can we guarantee those 2 people whose form an ordered pair? We need to make sure that every single possibility is counted for, and then we add 1 more person. This is the pigeonhole principle. Let's see. We don't need to actually define the pigeonhole principle, but just understand how to use it, basically. What the pigeonhole principle says is, say we have well, the literal definition is, say we have n holes, and we have k pigeons. If k is greater than n, and we want to put all the pigeons in a hole, and our goal is to ensure that each pigeon gets its own hole, there's going to be more than 1 pigeon in a hole if k is greater than n. So that's the pigeonhole principle. And we want to apply the pigeonhole principle for this question. So first, let's find how many total holes there are, or total places to put the pigeons, even though these are names. So how many total possibilities can we make? Well, the first initial and the last initial. So let's multiply. You have 26 choices for the first initial and 26 choices for the second initial. What is this? I think this is 676. So what does this tell us? We have 676 pigeonholes. And what do we know? For every pigeonhole to be full and for 1 repeat to be guaranteed, we need 677 students. So how many students do we have? So let's just write this out. So this many. And how many students do we already have? Okay. Now if we just subtract, and what is this answer? We get this many new students. You don't even need to know the pigeonhole principle, but you just need to think this through for this question. Like, for us to guarantee there's an overlap, we need 1 of every single combination, plus 1 more, because there's going to be overlap if you have 1 more. And by pigeonhole, we see we need at least 677, provided they're spread perfectly to guarantee. How many do we have? 348. Let's subtract. We need at least 329 more students. Number 4, that one tricked a lot of you. So the diameter was increased by 150%. What percent did the volume increase? So let's write the volume of this here. 4/3 pi r squared. I mean cubed. But this, I don't care about this. This is constant. So let's call this CR cubed for some constant C. What is that constant? 4/3 pi, but we don't care. So let's start with the original sphere. Let's say the original sphere, the diameter or original, let's say that has a diameter of 2r. So it's nice. So that tells us our volume is equal to c r cubed. Great. Now let's look at the diameter of nu. It's equal to 150% more. So our original, but we added 150%, which is 1.5 times 2r. What does this tell us our new diameter is? 5r. Okay, what does this tell us? Radius. Let's let this new radius be capital R. The radius is equal to 5r over 2, because it's half the diameter. Now, knowing that, let's find the volume again. The volume is equal to c big R cubed, which is equal to c little r cubed times 5 cubed over 8 cubed. What does this equal? 125 over 8. This should be 2. I jumped ahead. So, what is this equal to? Well, let's divide. Let's break this out. We get 15 plus 5/8, which is equal to 15.625. Now it's times by 100. So we know the new thing is 162.5% greater. But we want to find what percent did the volume increase. So at the end, we have to subtract 100. So we find it increased by 1462.5%. So yeah, for those of you who are really close, you forgot you have to multiply through per percentage. Okay. Now moving on to the last one, which is even more fun. Amira takes 4 blank cards and writes the letters and numerals shown in the figure on the front of the cards. Amira then flips over the cards, shuffles them, and randomly writes the letters and numerals shown on the back of the cards. What is the probability that the following statement is true for all cards? If a card has a letter written on one side, then the letter A is not written on the other side of that card. So you want to prove what is the probability that can happen. So what is that probability? So over the total and occurrences, how many times it occurs. So let's see, how many ways can we arrange these cards such that we follow this condition? That if the card has the letter on one side, A cannot be on the other side. Let's write down our front and back. First, let's find our total. So it's a bijection. We have a bijection here. Each one maps to only one thing on the back. So it's a 1-to-1 bijection. So what does this tell us? That we have a 9. How many choices for the 9? We can pair it up with 4. We have a B. How many choices left? 3 times 2 times 1, which implies it was 4 factorial. So there's 24 total ways. Now let's find how many ways that we can do it such if there's a letter on one side, A cannot be on the other. So we have an A on the front. Let's start with this case. What does this tell us? That we have to have a number on the back. But there's only one number over here. So what does this tell us? That A front and 2. So let's just take those out now because we know they have to be together. Now we have 9, B, 7, and M, S, A. Now we have an A over here. What can the A go with? The A can go with the 7 or the 9. But there's so few cases. Let's just write them all out. What can A pair with? If A pairs with 9. Okay, A and 9, what do we have? B 7ms. What does that tell us? There's two ways to arrange it. B can go with M or B can go with S. So if it's A and 9, we have two cases. And now if it's A and 7, we have 9BMS. Once again, two cases. So what does this tell us? We have four cases. We have four cases where it works over 24 total cases. What does this tell us? There's a 1/6 probability that for any random occurrence that we satisfy these conditions. Okay? You guys can take a small 5-minute break, work on the second set. You have until 6:20. I mean, 9:20. If you wonder why I keep screwing up with time, my computer's on Pacific time and I don't know how to change it. Yeah. Anyways, you have until 9:20, and yeah, you can take a small break, work on the next set. If you had any questions on this set, just shoot me a question. Okay, let's start problem set 2. Let me pull this up. See, there's quite a bit of geometry in here because I haven't been giving you guys much of that. There's a bit of probability, geometry you guys saw there, and some number theory in 5, which is a very, very difficult question. So, let's start with the first one. So we know he takes 8 shots. Let's just set up the system of equation. What does this tell us? That he made 8 shots and 21 points in total. Let's double this to get 2x plus 2y equals 16. Subtract y equals 5. What does this tell us? We made 5 3-pointers. We wrote so little, so I'm going to just do 2 right here. So we have point P. We have point P. Let's call this M comma N. Okay, we reflect it across the y-axis to obtain point R. This is it. Yep, point negative M comma N. And then we reflect it across. Oh, I did that in the wrong order. We reflect it across the x-axis first. It wouldn't have changed the answer, but you know. M comma negative N. Then we reflect it across. So let's just label the points P, Q, the x-axis to obtain negative M comma negative N. Okay, we have our triangle here. Let's write our side lengths. So we have M. So this is M. I mean, this is N. This is N. This is M. This is M. What does this tell us? Area of the triangle, 1/2 base 2M times height 2N equals the area. And what did we establish the area as? We established the area as 80. So what does this tell us? Well, it's 2MN equals 80. So it tells us MN equals 40. Now we want to find the least possible value of N plus M. Well, how do we do that? Well, we want to find N times M equals 40. And if you don't know, the greatest value occurs when M equals N. So what does this tell us? Let's substitute M squared equals 40. M equals 2 root 10. N equals 2 root 10. What does this tell us? M plus N, absolute value. Which tells us M plus N, absolute value, with a 4 root 10. So your answer is 4 root 10. Oh, but wait. They're asking for the least possible value of M plus N. So now we've established M equals N. Now we know this point is 4, 10. But let's remember, we can put M and N anywhere. So, what does this tell us? The least possible value of an absolute value. What's the smallest possible value of an absolute value? 0. So we've just established, for this case, M equals N. But is there any way where we can have M times N equals 0? No, M times N are just lengths. And lengths are always positive. But the coordinates don't have to be. So actually, it'd be more precise if we wrote our area as equal to the absolute value of M times the absolute value of N equals 40. So what does this tell us? If we let M equals negative N, we can still have M equals 2 root 10. But we can have N equal negative 2 root 10. And what does this tell us? This still gives us the exact same triangle, just changed. Because now we start here. We reflect across the x. We still get our triangle, same area. But now what can we do? M plus N. M plus N is equal to M minus M, which is equal to 0. So we've shown the least possible value of M plus N is actually 0. Despite what it seems like it's root 10 plus root 10, right? Because we got that side length, M, N, they're both root 10. But no. we have to also take into fact that is an absolute value, and the coordinates don't necessarily have to start as positive numbers. So then we have to realize, what is the minimum of an absolute value? It's 0. And we need to see it. Can it be obtained? Here, yes, it can. The minimum is 0. On to number 3. We have our circle. O. And then we have our little square that we put in it. What do we know about this? You know that P, O equals 2. Let's call this R, S, T. What is the area of the shaded region? So we have PO, okay. We know this is 4. What else do we know? This is 6. What does this tell us? We know this is 4. And if we know this is 4, this is 2. We're seeing some similarities here now. But we want to find the area of the shaded region. How do we find the area of the shaded region? We have to find the area of the non-shaded region. But what is the area of the non-shaded region? Wait a minute. Okay. We have this. Doesn't look that bad. We also have this. And these are both radiuses, now we realize. And now what do we have? We have this really awkward looking shape that we just reduced to a part of a circle and 2 triangles. And we know how to find the area of a part of a circle and 2 triangles. Okay, so we can work with that now. But what is this little section? Let's think again. Wait, this is a right angle. So's this. And these side lengths are the same. You know what that means? This and this are congruent by, well, let's show they're congruent first. What is the radius? And this is a right triangle. So they are congruent by actually hypotenuse length. So we don't have to show that exactly. So now we know this and this are exactly the same. So what does this tell us? It tells us this is theta, this is 90, this is 90 minus theta. And by that logic, this is 90 minus theta, this is theta. This angle must sum to 180, and we already have 90 degrees. What does this tell us? This is a right angle. Now we have everything we need. We know this is a quarter of the circle. And all we have to do is find the radius to find that area. So what is the area of these 2 congruent triangles? And we know they're congruent by hypotenuse length. These are right triangles. Well, let's start off with the area of 2. So we have 2 of these, and the area of one of them is 1/2 base times height, which is equal to 8. Okay? Now we have that. Now let's find the area of this quarter of a circle. What is a radius? Well, this is a right triangle, right? So this would be the hypotenuse. The radius is equal to 4 squared plus 2 squared root, which is equal to square root 20. The area of 1/4 of a circle is equal to 1/4 pi r squared, which is equal to 1/4 pi 20, which is equal to 5 pi. And now, go to the back. Area shaded equals total minus white. What does that mean? What is the total area? Well, it's a square with side length 6. So you get 36. And what did we establish the white here as? 8 plus 5 pi. But minus 8 minus 5 pi equals 28 minus 5 pi as your shaded region. Okay? If there's nothing there, let's move on to number 4, another terrible geometry question. So it's 2023. Hopefully you know this, because it's really helpful to know this. Those are the factors of 2023. Wait, this is a right triangle. 17 works very, very well with right triangles, because what do we know? We know that this exists, an 8, 15, 17 right triangle. That's a thing. But first, let's draw this right triangle. And it's similar to this triangle. Well, let's think about it. What is this triangle? This is a 40, 75, and let's find the last side. The last side is 40 squared plus 75 squared square root. What does this equal? This plus, what's 75 times 75? What is it? 5625. Okay, what does this equal? This is equal to 7225. Wait a minute. The square root of this, that's 85 squared. So it's 85. So we know this. And we know it's similar to this. So let's get to the simplest case. Let's divide all the sides by 5. Look at that. You get your 5 times 8, 5 times 15, and 5 times 17. We found our factor of 17. And that's really important because we have all the sides have to be integer lengths. Knowing that, let's work with this. Let's make a small triangle. Let's call this ABC. And let's make this the smallest case possible. Great. Now, any of these sides could be 2023, but they all have to have integer lengths. So in reality, only BC can have length of 17, which means, what does this mean? We have to multiply this by 7 times 17. And we have exactly what we want. Okay. What does this also mean? We have to multiply every side by 7 times 17. And then we get it there. Yeah. Oh, this is an 8. This is what we have now. We have, what's 7 times 17 times 8? This doesn't matter much. I'm just going to bring out a calculator. You don't actually get one for the math guns test, but I'm lazy. So you get a triangle with lengths. 952, 1785, and exactly what we wanted, 2023, through similarity. But they want the area. Once again, I don't want to do this by hand. I'm lazy. So I'm going to use a calculator. So the area is equal to 849,660. So what did this require? This question wasn't hard if you knew 2023 is 7 times 17 squared. And you know the 8, 15, 17 right triangle. Because you're going to realize, wait, this is an 8, 15 times 17 triangle. Let's reduce it to its simplest form. And now 17 must be a factor of one of the sides. And we don't want to use one of these sides because it gets horribly messy. So let's make it this, because we want the smallest possible length for the 2023. So in theory, we want 2023 to be the biggest so that we get the smallest possible case. And that's what we did. So we get the area is this. And for the last question, we have our sequence. A1 plus A2 plus A3 plus A4 plus A5 plus A6. It's a geometric sequence of positive integers, which every term is less than 2023. What does this tell us? We have, well, R, so A1 plus A1R plus A2R squared plus A3, wait, these are all the same A's. It's not a Newton sum. Okay, so we want to find the maximum sum of this, because this is a geometric sequence. Let's call this sum S. But this is really messy. We don't like this. Let's multiply S by R. What does this give us? Well, we have RS is equal to 0 plus AR plus AR squared plus AR cubed plus AR to the 4th plus AR to the 5th plus AR to the 6th. Wait, there's a lot of overlapping terms here. So what if we did RS minus S, which is equal to R minus 1 times S, which equals AR to the 6th minus A. Wait, this looks nice now. We divide both sides by R minus 1, get the original sum we wanted is equal to AR to the 6th minus A over R minus 1. But what is A? A is the starting term. So what does this tell us? R to the 6th minus 1 times A1 is equal to R minus 1. Okay, great. We have the formula for our sum now. This is the sum of a bounded geometric sequence. Something you should memorize. The bounded geometric sequence sum is equal to, for A1, all the way to, from A0, all the way to AK, such that AN equals RN times some constant C. So AN equals C, R to the N. The sum is equal to A0 R to the N minus 1 over R minus 1. So that's the formula for a limited sum. So now we have our formula. So we can throw away this page now and just write our formula here. Okay, this is what we have. So how do we maximize our sum? Because we want the greatest sum. Well, and what do we also know? The largest term is 2023. So let's think about it. So the largest term is A1 R to the 5th. First, let's start with possible R's. We know that this is geometric sequence of positive integers. What does this tell us? We're in a ring of integers. All the integers that enter, all inputs and outputs are integers in this case. Because an input of a non-natural number results in a non-natural output. Essentially, that's what we're saying. So let's think about it. What else do we want? We want R to the 5 to be as large as possible while having R minus 1 being as small as possible. What does this imply? We want A1 to be as large as possible. We want the largest possible starting term. What else do we want? We also want the smallest possible ratio. How do we get there? Well, let's think about it. Let's just think. We have this sum. And let's experiment with ratios. Let's just let A1 equals 1 for here. So, if we have a ratio of 2, the largest term is equal to A1, 32A1. If we have a ratio of 3, 3 to the 5th, what is 3 to the 5th? 9 times 9, 243A1. And now, let's say we have R equals 4. We have, what is 4 to the 6th? And 4 to the 5th, 1024. Okay, and let's just say we stop there. Because if we go, let's just do one more so we can break the barrier, though. 5 times 5, okay. So we know this is 3, 1, 2, 5. So, 2023. So if we're picking an integer ratio, none of these seem nice to work with. Let's just say, we're working around. Let's minimize our R. What's something we can do to minimize R? Well, 2023, that's a really, really annoying number to work with. But still, let's think about it. Let's just say, let's just multiply up a bit here. What is this? This becomes 729 and 21 something something. So that's too big. So now we're stuck in this a really annoying spot where we can't work with anything. Unless, what if we picked a ratio to be, well, without loss of generality, let's just say our ratio is positive because and greater than 1. Because if it's less than 1, we can just flip the sequence around and get the same result. Now we're working with this. We're saying, what if we had a non-whole number ratio, though? Because, like, say if we had ratio of 4/3, that could still work. So we're thinking about this now. Let's think. 2, 4, 3. Okay. What's the largest possible number we can have here? Well, obviously we want to see. Let's multiply this by 8. We get 6 plus 3, 2 plus 24. What does this equal? 1944. This is pretty darn close to the max. In fact, this is the largest number that we can work with. And knowing that, this is perfect. We have 2 with 3 to the 5th times 2 squared. But now, as we said, working forward with a ratio m over n is the same as working backwards with a ratio n over m, because that's how series work. Multiplication goes forward and backwards. What does this tell us? Let's work backwards now with a ratio less than 1. Okay, so we have 3 to the 5th times 2. We could just have a common ratio of 3, easy peasy. But we don't want that. That's bad. Why is it bad? Because our number's too small now. But we want to maximize the starting number. So let's multiply the top by something. So let's say we had a common ratio of 2/3 going down. Because that's nice to work with. And that multiplies out all the 3's without throwing away all the 2's. By the way, this is 2 to the 3rd. So what does this tell us? Well, let's just work down. I'm using a calculator because I'm lazy. We're just going to keep multiplying by 2/3. We have 256. Now let's think. Could we pick any starting number bigger than 256? So we have a ratio of 2/3. Is there any way to create a smaller ratio using these whole numbers? Any larger ratio? No. What does this tell us? 2/3 is the ideal ratio, which means we also found the ideal starting point. Because there has to be at least 5 factors of 2 on the bottom. So we found it. We found our A1, which is 256, and our ratio. So our final sum. So r to the 6 minus 1, r minus 1, A1. What did we establish? R is equal to 3/2. Because now we have to flip it again, because we're moving forward. And A1 is equal to 256. What does this leave us? This leaves us with 3/2 to the 6th minus 1 times A1 over 3/2 minus 1. I'm using a calculator again. 279 for 64 minus 1 times 256 over 1/2. And for this, I'm just going to use a calculator for all of it. We get 665 over 64 times, let's bring the 1/2 up, 512. What is this? Our maximum sum is 5,320. Oh, I went way over. I just wanted to finish up these problems. This was a hard set. Today was a hard set. Probably the hardest of the whole time. All the rest other sets, I promise, are going to be easier. This was just more in a favor of math counts. These were all old math counts problems. Actually, from this year, these were math counts problems from the chapter round, and a few from the state. So if you do compete in math counts, you're gonna be expecting problems like this. But yeah, that's it for today. Sorry for going way over, and yeah, you guys are good to go.